Okay. So I was asked to give an overview or give a talk on a project we've been working on, which is named towards a complete simulator for sub-millimeter single-dish observations. Or it's a simulator tool we developed, which I developed during my PhD at ESO, which is named Maria, which resulted in a paper you can see on the bottom right. And Maria is a very generic simulator tool, and I'll give a quick overview on how to use it and what you can use it for. But I really want to stress that the development of Maria, this novel simulator for forecasting single-dish sub-millimeter observation, was really a joint effort. Like a lot of work is done by Thomas Morris, who is a grad student at Yale, and now a lot of the effort is being driven by Jonas Rutzinger, which I will come back to that work later. So it's not really just me sitting in a room coding stuff up. It was really a collaborative effort by a lot of people. So, right, we were setting out to create an observatory tool, a simulator tool, with three specific goals in mind, right? We wanted to make realistic observations from simulations and able to link telescope designs with scientific output, so number of detectors with scientific merit, link observation with theories, have an apple-to-apple comparisons on the tool you want to use, and the tool itself must be very versatile and easy to use. This is really the goal of this whole project, of this simulator tool, because in our opinion, it didn't really exist yet. So in order to go over these 3 points, I will briefly talk about 3 topics. I will talk about the evaluation of Maria, which we evaluated with real telescopes that are operational now. Then I will show some predictions, which we did for AtLAST. And then I will give some overview on what we are working now. I hope that fits within the next 15 minutes. I think it will. Okay, the simulator itself consists of roughly 4 components. You give it an input sky. So this is just your astronomical signal, which you want to observe. Then it has this simulated evolving atmosphere, which is the main noise contributions in your observations, which is time specific, evolves over time, and location specific. Then you have to give it a telescope, an instrument or array design, and a plan, so how you want to observe through the atmosphere over your astronomical signal. So these are roughly the 4 components, and I'll quickly introduce them before evaluating the tool itself. Because in an ideal world, you want to observe something like this, right? So I study galaxy clusters. This is the hot gas in a simulated galaxy cluster. But in reality, all you see is something like this, which is just the atmosphere. It's roughly 7-8 orders of magnitude brighter than the astronomical signal which you're interested in, at least for me. If you remove the atmosphere, like let's say you remove the common mode, where here you can see just because of air mass. If you remove this common mode, you still are left with this, right? The atmosphere is a turbulent, emissive thing. It changes, it evolves over time, and it fluctuates. And even these fluctuations are much brighter than the atmosphere itself, than the astronomical signal itself. So what you need to do when you scan with a bolometer array, for instance, you need to scan on source and off source fast enough, faster than the atmosphere changes, so you can also remove that as a common mode. So how that would look like if this is the galaxy cluster I was talking about, you would scan in these sort of Lisa-Joule daisy scan patterns where all of these detectors go on and off source. So this is sort of the setup which we need to mimic. And then for each of these detectors you saw, you get these sort of time ordered data. So I can show you an example of a time stream similar to the Green Bank telescope, which is a large single dish in West Virginia, where you have on the y-axis the temperature or the amplitude of your signal, on the x-axis time, right? So this is just for a single detector. This is what we want to create to really have apples-to-apples comparisons. When we want to evaluate the tool, we don't necessarily want to recreate the exact observation, but we're more sort of interested in statistical properties of this signal. So what we're going to do is going to look at the power spectra of it. And power spectra sometimes sounds a bit confusing, but we have a very good intuitive of the components to build it up, right? So if you have a telescope, a big part of the telescope is just your white noise, which is flat in your power spectra distribution, which is just, let's say, thermal noise in your detectors. And often you have this 1/f noise, which is your readout or drift noise. And then you have this atmosphere component, right? Which is steeper and much brighter than your white and drift noise. And all much below this is astronomical signal at much lower amplitudes. So if you take the power spectra of what is seen on the right side, you can see something like this, where you again have the atmospheric part on the left part, then you have this drift noise in the middle, and then white noise on the right side. And this is a simulated observation. And here I overlay a real Mustang 2 observation, as if observed on the same day with the same weather conditions. So it's a remarkable match. We just don't have these peaks and spikes which we have on the high sampling rate part of the power spectra. So what you then want to do, this is great, it really overlaps. What you then want to do is you want to make maps, because we don't really think that much in power spectra space in Fourier domain. So what we do, if you have these time streams, you can make a simple mapper by putting a high and low pass filter over these time streams. So you sort of filter out the low frequency part, so filter out the atmosphere, and high frequency part, all these spikes. And then you just bin the signals together and remove the carbon mode while you're at it. And then you get these maps which you show here on the right side. With on the top one, a real observation. So this is a noise map, and on the bottom one, a synthetic one. And they really, really do look similar. So we didn't put an hydrodynamical simulation or an output from hydrodynamical simulation map behind this, but we can do this as well, right? So let's say we have, again, a galaxy cluster where you have a shock front, a pressure discontinuity, which is of scientific interest to me. And on the left side, the subhalo. Then we can scan over it with Maria for 45 minutes. And then you get something more like this, where the shock front is not as good detectable anymore, and the subhalo is effectively gone. We can model this, we can extract the flux, fit some Gaussians to it, and then you still sort of see the shock front if you remove the bulk motion, but it's really hard to probably study this. Now you can play with a little bit with Maria. You can increase this white noise sensitivity and increase the mapping speed a little bit. And then you have, for instance, another telescope design or instrument design, which, for instance, named Mustang 3. So this is all for bolometric observation. And then by slightly increasing the sensitivity and the number of detectors, you can really see you can improve on your results. So this was part of a proposal. So here we just simply increase the sensitivity of detectors, increase the field of view, and the mapping speed. You can really see that we're able to do a lot more science. So it's just tweaking telescope designs, and you effectively get your scientific output different. Okay. So this evaluation we've shown with Mustang 2, which is just a relatively smaller instrument on the Green Bank telescope. Let's try and use this now for AtLAST, which is a much bigger telescope, right? So here are just some numbers that compare Mustang 2, which the maximum frequency it can observe is 100 gigahertz, with AtLAST, which is the lowest frequency it can observe. So it's not a real good comparison, but it does give the idea across. And you really need to look at the detector count, for instance, the bottom row. Mustang has 230 detectors, and now we're going to simulate 50,000 detectors, right? So this is also a big jump in computational power, which you need to code up properly. Also, the field of view is obviously larger, and we increase the white noise level sensitivity to be roughly background limited. So let's say we have this cluster. Now, we're not going to make the same observation of the cluster because with AtLAST, you can do so much more science, which is not capable now. So let's zoom out and let's put this to scale and observe a galaxy cluster in the local universe, which is just not observable with the current observations or facilities that we have. So for instance, here I show mock ALMA observations on the shock front on the top in the middle, and mock Mustang 2, and the mock Mustang 2 observation doesn't result in any detection simply because the common mode of the atmosphere gets confused with the common mode of the cluster. So this cluster is not detectable with anything we have today, and it's over-resolved with, for instance, ACT or something. But if we increase the telescope specifics within Maria, so we have 50,000 detectors and increase the white sensitivity and the mapping speed and everything, we get to something like this. So now we suddenly can detect this cluster and really do cluster astrophysics with it, similar to how, for instance, Rosita does this in the X-rays. This is really exciting.
1 minute.
And here I just, okay, thank you. And here I just changed the telescope designs, right? I didn't put like Gaussian white noise over the image. So it's really starting from fundamentals. Okay, in the last 5 minutes, I want to briefly touch upon, so all you can find is what I showed before. It's already published in my paper, or for instance, the previous one from Luca. Now I want to show some stuff we're currently working on, which is also up for discussion if you want, which is still in preparation. So we're still working on this, but I thought it would be fun to show. The question that comes up if you're really interested in this big 2-degree field structure, is how to still best remove the atmospheric component. Because in the previous example, we did a very naive map making where we just Fourier filtered the data, but you really don't want to do that. You don't want to Fourier filter it because you also lose flux and you increase artifacts into your imaging data. Now, Maria is already compatible with, for instance, maximum likelihood approaches. We really want to try to beyond that and test how well we can remove the atmosphere. Because one of the advantages of building a very large single dish is that the measured atmosphere with a large aperture is much more correlated than when you build smaller dish sizes or smaller aperture sizes. So, for instance, we tested this with Maria for 42 centimeter apertures, 6 meter apertures, and 50 meter apertures. And the common mode, so just focus on the blue points, really does increase, meaning there's more correlated atmosphere. And the reason is just because of how beams propagate. This is simply geometry. If you have a 50-meter single dish, your beam, your near field lies very far, way above the atmosphere. So your beam just propagates as a single column through the atmosphere. So when the wind moves with a constant velocity passing your aperture size, it only changes a fraction. So with every integration, every snapshot, you effectively see the same atmosphere. And if you see the same atmosphere, the idea is you can remove this properly. But this is easier said than done. So what we're experimenting with is this nifty application, which is a Gaussian process framework, in which we effectively using Gaussian random processes to model the power spectral distribution. And like I told you before, we sort of already know which components are in the power spectra. So if we can model this, let's have an initial power spectra and disturb it with Gaussians. We can sample from that model posterior distribution to create a map from our observations. So this is a machine learning approach to going from time-ordered data to map space. And to give you an example, input is a Maria simulation, so we really know, right, the differences between the astronomical signal and the atmosphere because we simulate them separately. So on the left, you can see the input model for Maria. The middle part is learned by the Gaussian processing, and on the right side, you can see residuals. And the residuals are on the sub% level. So that's really working. And my final plot, which I can show you too, is then how the map comes out. So here I'm going to increase the complexity of the modeling. So you have to iterate over, you have to learn which Gaussians fit the power spectral distribution best. So on the left side, you're going to see the mean map predicted. On the right, on the middle side, you see the truth map, which is shown on the right, versus the predicted one. So it's like a residual map or a fidelity map. And now I'm going to play it, and we're going to slowly increase the complexity. And you can see that this process is really learning the astronomical signal really well. Now, at some point, we're going to start overfit, and we're going to introduce modes which are a little bit larger. So this is still sort of work in process, but this is tested on Mustang data, and we are currently trying to sort of handle the large data rates that AtLAST is going to produce and be able to do that. But we're very confident that we will manage to be able to apply this sort of correlated sort of Bayesian inference framework on how to go from time-ordered data to map space also when we have 1 million of detectors instead of 200. Okay, so to give a go back, a bit of a summary, Maria is a novel simulator for forecasting single dish with millimeter observations. It is able to link telescope designs like number of detectors, white noise sensitivity, mapping speed, all this kind of stuff to your scientific output or your merit, scientific merit. Herefore, you can also use the same tools you use for observations to the simulation. So you have an apple-to-apple comparison to really understand what you're looking at. And Maria is very versatile and easy to use, at least as easy to use as it is with real data. And to help you people with that, we built this website, which is thomaswmorris.com/Maria, where it explains how the installations, there are a bunch of tutorials, supported site, and a list of the papers, which also use Maria papers. So I can definitely recommend you go there. The code is still under development, right? We're the three of us are just working on this sporadically. So we can definitely use your help, use it, download it, play around with it, and let us know if you find anything funky, or if you don't and you really like it, you can also let us know. That would also be appreciated. Thank you very much.